Okay. So next I need to tell you how to invert matrices. So what's the point of matrices? It's that it gives us a nice way to think about these changes of variables. And in particular, if we know how to express u in terms of x, maybe we'd like to know how to express x in terms of u. Well, we can do that because we've learned how to solve linear systems like this. Okay? So in principle, we could start working, substituting, and so on to find formulas for the x1, x2, x3 as functions of u1, u2, u3. And the relation will be, again, a linear relation. It will, again, be given by a matrix. Well, what's that matrix? It's the inverse transformation. So it's the inverse of the matrix A. So we're going to learn how to find the inverse of a matrix directly. Okay. So the inverse of A, by definition, it's a matrix M with a property that if I multiply A by M, then I get identity. And if I multiply M by A, I also get identity. The two properties are equivalent. So that means, if I apply first the transformation A, then the transformation M, I undo the transformation A, and vice versa. These two transformations are the opposite of each other. Well, I should say the inverse of each other. Okay? So for this to make sense, we need A must be a square matrix. Okay, so it must have size n by n. It can be any size, but it must be the same number of rows as columns. And it's a general fact that, you will see more in detail in linear algebra if you take it. So let's just admit that. So the matrix M we will denote by A inverse, like this. Okay? And then what is it good for? Well, for example, the solution to a linear system. So what's a linear system in our new language? It's a matrix times some unknown vector x equals some known vector b. Well, how do we solve that? We just compute x equals A inverse b. Why does that work? How do I get from here to here? Let's be careful. Oh. Okay, well, I'm going to reuse this matrix, but I'm going to erase it nonetheless. I'll just rewrite it. So I'm saying if AX equals B, then let's multiply both sides by A inverse. A inverse times AX is A inverse B. And then, well, A inverse times A is identity. So I get X equals A inverse B. Okay, that's how I solved my system of equations. So if you have a calculator that can invert matrices, then you can solve linear systems very quickly. Now, we should still learn how to compute these things. Yes? How do I know that A inverse will be on the left of B and not after it? Well, it's exactly in this derivation. So if you're ever not sure, then just reproduce this calculation. See, to get from here to here, what I did is I multiplied things on the left by A inverse. And then these guys simplify. If I had put A inverse on the right, I would have AX A inverse, which might not make sense. And even if it makes sense, it doesn't simplify. So, I mean, the basic rule is, you have to multiply by A inverse on the left so that it cancels with this A that's on the left. That's correct. So, and in our usual way of dealing with matrices, where the vectors are column vectors, I mean, it's just something to remember that if you have a square matrix times a column vector, I mean, the product that makes sense is with the matrix on the left, the vector on the right. The other one just doesn't work. It's not sized. You cannot take x times A if A and x, if A is a square matrix and x is a column vector, this product makes sense. The other one doesn't make sense. It's not the right size. Okay.